Every star that burns, every planet that spins, and every atom that hums in the void is shaped by a force we cannot see. It's silent, invisible, and yet it's everywhere. This force weaves through galaxies like a hidden thread, sculpting the light of distant pulsars, driving the fury of solar storms, and even shielding our fragile world from deadly radiation. This is magnetism, one of nature's most mysterious and least understood forces. For centuries, we thought magnetism was just about compasses and lodestones, a simple curiosity of navigation. But as our telescopes peered deeper into the cosmos, a shocking realization emerged. Magnetic fields aren't rare, they're universal. They are the invisible architects of the cosmos. Imagine looking at a spiral galaxy, like our own Milky Way. You see the graceful arms, the bright stars, the dark dust lanes. What you don't see is the immense magnetic field, a cosmic web that guides the very gas that forms those stars. It acts like a shepherd, corralling clouds of plasma and dust, helping them collapse under their own gravity to ignite new suns. Without this magnetic shepherding, star formation would be a far more chaotic and less efficient process. The beautiful, orderly spiral arms we admire might not even exist. The magnetic field is what gives the galaxy its structure, its stability, and its ongoing ability to create. Now let's zoom in on one of those stars, our own sun. It's a churning ball of superheated plasma, and this constant motion generates an incredibly powerful and complex magnetic field. This isn't just a static field like a bar magnet. It twists, it tangles, it snaps. When these magnetic field lines get overly twisted and suddenly realign, they release colossal bursts of energy. We see these as solar flares and coronal mass ejections, events powerful enough to send billions of tons of charged particles hurtling through space. And this is where Earth's own magnetic field becomes our hero. Our planet's molten iron core acts like a giant dynamo, generating a protective magnetic bubble around us, called the magnetosphere. When a solar storm hits, this invisible shield deflects the vast majority of those harmful particles. You can actually see this cosmic battle playing out in the sky as the beautiful auroras, the northern and southern lights. They are the visible evidence of our magnetic field working overtime, protecting our atmosphere, our technology, and all life on Earth from being stripped away by the solar wind. Out at our world would likely be a barren Mars-like rock. But the influence of magnetism extends to the most extreme objects in the universe. Take pulsars, the superdense, spinning remnants of massive stars. They have magnetic fields, trillions of times stronger than Earth's. As they rotate, they sweep beams of radiation across space, like cosmic lighthouses. It's their magnetic fields that channel and accelerate particles to near the speed of light, creating the very beams we detect. Even more astonishing are magnetars, a special type of neutron star with the most powerful magnetic fields known to exist. Their fields are so intense, they can distort atoms and cause starquakes on their surface, releasing more energy in a fraction of a second than our sun will in thousands of years. From the galactic scale down to our planetary shield, magnetic fields are the unsung heroes of the cosmos. But this brings us to one of the biggest questions in modern astrophysics. Where did it all come from? How did the universe get magnetized in the first place? One theory suggests that tiny seed magnetic fields were born in the fiery chaos just moments after the Big Bang. These primordial fields, though incredibly weak, were then stretched and amplified over billions of years by the rotation of galaxies and the turbulent motion of plasma. Growing into the cosmic structures we see today, this is the dynamo effect, the same principle that powers the magnetic field of Earth and the Sun. But playing out on an unimaginably vast scale, it's a process of taking a tiny magnetic spark and fanning it into a galactic fire. So, the next time you look up at the night sky, remember the unseen architecture holding it all together. It's not just gravity pulling things in. It's magnetism pushing, guiding, and structuring the universe. It's the silent force that sparks stars, shields worlds, and paints the sky with light. The story of the cosmos is written not just in matter and energy, but in the invisible lines of magnetic force that connect everything. To understand how magnetic fields shape our universe today, we have to rewind the clock. Way back, back to the very beginning, before galaxies, before stars, even before the first atoms formed. The universe was a super-hot, glowing sea of charged particles, cosmic plasma soup. Think about it, just 380,000 years after the Big Bang. Things finally cooled down enough for protons and electrons to get together and form the neutral hydrogen we know and love. But in those very first moments, everything was an electrified fluid. And here's the key. In plasma, electric currents naturally give birth to magnetic fields. This was the universe's very first act of cosmic magnetism. In that early chaos, tiny ripples and turbulence in the plasma may be from quantum fluctuations or the incredible expansion of cosmic inflation, space into microscopic loops of current. Each of these loops generated an incredibly weak magnetic field, seed field, so faint we could barely detect it even with today's technology. But these tiny seeds were everything, because in an expanding universe, even the quietest whisper of magnetism has the potential to grow into a roar. As matter started to clump together, drawn by gravity, to form the first stars and galaxies, these seed fields were pulled along for the ride. They were stretched, twisted, and amplified. Just like a single musical note resonating and building into a grand symphony. Scientists have a name for this process, the cosmic dynamo. It's the exact same principle that powers Earth's magnetic field, keeping us safe from solar winds. But scaled up to galactic proportions and playing out over billions of years, when the first stars finally ignited, their nuclear furnaces stirred up powerful internal currents and unleashed stellar winds, supercharging the magnetic landscape around them. Then came the supernovas, the explosive deaths of massive stars which flung magnetized material far out into interstellar space, seeding the cosmos even further. And let's not forget the monsters of the universe, black holes. Their powerful accretion disks, swirling whirlpools of matter being pulled in, became cosmic forges. They spun and stretched magnetic field lines until they snapped, releasing mind-boggling amounts of energy in colossal jets that could blast across thousands of light years. Magnetism, it turns out, became a universal consequence of motion and matter. It's as fundamental to our universe as gravity itself. Wherever charged particles moved, magnetic fields were right there with them. But the story gets even more profound. For decades, scientists thought of magnetism as a secondary player, mere side effect of more fundamental forces like gravity and electromagnetism. But as our telescopes and instruments became more sensitive, a radical new picture began to emerge. We started seeing that the very structure of the cosmos, from the vast cosmic web that connects clusters of galaxies to the mysterious halos of dark matter, seems to be threaded with gigantic magnetic filaments, spanning millions of light years. Magnetism isn't just reacting to the universe's shape, it might actually be helping to create it. In our modern universe, we see this in action everywhere. Magnetic fields guide the birth of new stars by controlling how clouds of gas collapse. They act like cosmic highways, channeling high-energy cosmic rays across the galaxy. They sculpt the beautiful, intricate shapes of nebulae. They even influence how entire galaxies rotate. They may be invisible, but they are anything but inactive. You can think of magnetic fields as the cosmic glue, binding plasma and motion together to create order out of chaos. So if these fields are everywhere, permeating everything, how on earth do we actually see them? How do we measure something that is invisible and find the ancient fingerprints they've left across the cosmos? I'll answer that. You have to turn to some of the most powerful tools in modern astronomy. Radio telescopes that can detect faint signals from across the universe. Pulsars that act like cosmic lighthouses, and the subtle flickering whispers of polarized light. These are the tools that allow us to finally see the invisible. Next time, we'll dive into the magnetic monuments of the universe, the spinning pulsars, the violent solar storms on our own sun, and the magnificent fields that wrap around entire galaxies. We'll explore the cosmic engines that reveal exactly how the invisible hand of magnetism shapes the universe we see around us. Magnetism. It's an invisible force, but its fingerprints are all over the cosmos. Some of its signatures are subtle, gently guiding vast clouds of gas. Others are dramatic, violent, and impossible to ignore. To truly understand the magnetic might of the universe, we have to start with its most extreme engines, pulsars. Imagine a star far more massive than our Sun, reaching the end of its life and exploding in a brilliant supernova. What's left behind is a pulsar, a rapidly spinning neutron star. In its core, matter is crushed to densities 1,000,000,000,000 times greater than anything on Earth. And within these tiny spheres, often just 20 kilometers across, magnetic fields reach staggering intensities, trillions of times stronger than any magnet we can create. These fields aren't just sitting there, they rotate, they twist. And they funnel charged particles into powerful beams of radiation that sweep across the galaxy like a cosmic lighthouse. Astronomers detect these beams as incredibly precise pulsing signals, making them the universe's most accurate clocks. But beyond their mesmerizing regularity, pulsars teach us something fundamental. Magnetism can completely dominate matter itself. In a pulsar, magnetic pressure shapes the star's atmosphere, accelerates particles to nearly the speed of light, and powers phenomena that push the very limits of our understanding of physics. The force is invisible, yet its effects are unmistakable, a cosmic monument to magnetic power. Closer to home, our very own star puts on a spectacular magnetic show. Solar flares and coronal mass ejections are magnetic phenomena on a grand scale. Deep beneath the sun's surface, churning currents of superheated plasma act like a giant dynamo, twisting magnetic field lines until they become a tangled mess. Eventually, the tension becomes too much. The lines snap, unleashing billions of tons of charged particles that hurtle through space at incredible speeds. These events might seem distant, but when Earth lies in their path, we feel the impact. These magnetic storms can disrupt our satellites, interfere with communications, and, on a more beautiful note, produce the spectacular auroras, the northern and southern lights, painting our night skies in radiant ribbons of color. It's a vivid reminder that we live within the magnetic influence of our star. But stars are only the beginning. On a galactic scale, magnetic fields weave an invisible framework that shapes how entire galaxies evolve. The magnetic fields within a galaxy like our Milky Way are much weaker than those of pulsars or stars, about 1/millionth of a Tesla, yet they stretch across tens of thousands of light years. They thread through the spiral arms and extend into the vast halo regions surrounding the galactic disk. These fields are crucial. They influence the motion of high-energy cosmic rays. They guide the flow of interstellar gas. And they even affect where and how new stars are born. Without these invisible forces, galaxies might not form their elegant spiral structures, and stars wouldn't form in the familiar patterns we observe across the night sky, even beyond individual galaxies. The cosmic web, the vast network of filaments connecting clusters of galaxies, appears to be magnetized. Using powerful radio telescopes, astronomers have detected faint emissions coming from these filaments. This is evidence that charged particles are spiraling along immense magnetic structures that stretch across millions of light years. It paints a picture of a universe threaded together like a giant lattice, an invisible scaffolding that is fundamental to the grand architecture of the cosmos. So, from the spinning heart of a dead star, to the violent eruptions of our sun, to the gentle but persistent fields that guide the evolution of galaxies, magnetism is truly everywhere. It's a force of both extremes and subtleties, shaping structures across an incredible range of scales, from the tiniest subatomic particle to the largest clusters of galaxies. And even though we've discovered these magnificent magnetic monuments, they seem to raise more questions than they answer. How did such organized, large-scale magnetic fields arise so early in the universe's history? Why do some galaxies host strong, coherent fields, while others appear completely chaotic? Is there some undiscovered universal principle guiding the formation and evolution of cosmic magnetism? These monuments, the pulsars, the solar flares, and the vast galactic fields are far more than just scientific curiosities. They are undeniable proof that magnetism is a fundamental architect of the cosmos. It's a force that silently orchestrates motion, energy, and structure on scales we are only just beginning to comprehend. Even as we map pulsars, trace solar storms, and chart the magnetic fields of entire galaxies, one profound question continues to haunt astrophysics. Where did all this cosmic magnetism come from? The universe is old, nearly 13.8 billion years, yet the first evidence we have of large-scale magnetic structures appears astonishingly early in its history. When we look at distant galaxies, seeing light that has traveled for billions of years to reach us, we find coherent magnetic fields already in place when the universe was less than a third of its current age. How on earth did these fields form so quickly? Current theories suggest the cosmos began with what are called primordial seed fields. These could have emerged from quantum fluctuations during inflation, that incredible period of exponential expansion in the first fractions of a second after the Big Bang. In these models, the tiniest ripples in the quantum vacuum were stretched across vast cosmic distances, leaving behind incredibly feeble magnetic imprints, weaker than a trillionth of a Tesla, making them almost impossible to detect today. Yet even such faint seeds could have been the start of something big. Through a process called the cosmic dynamo, the constant motion and turbulence in ionized gas over millions of years can amplify weak magnetic fields, twisting and stretching them into the coherent structures we now observe in galaxies. But the dynamo theory itself raises more questions. For it to work efficiently, it needs motion, things like spinning galaxies, turbulent gas clouds, or violent stellar explosions. The problem is, some of the earliest galaxies appear fully magnetized before these kinds of dynamics could have fully developed. This suggests that either our models are missing something, or there's an unknown mechanism that dramatically sped up the growth of these magnetic fields in the early universe. Magnetism might also have roots hidden within the cosmic microwave background, the faint afterglow of the Big Bang. Tiny temperature differences in this ancient light might carry the imprints of primordial magnetic fields. But trying to tease out these signals is extremely difficult. The fields would be incredibly weak, and the cosmic microwave background itself is full of noise from other sources. Even with our modern tools like timing the pulses from distant pulses or measuring how polarized radio waves get twisted as they travel through space, we're only seeing part of the story. Magnetic fields interact with charged particles, cosmic rays, and turbulent flows in incredibly complex ways. A single magnetic field can thread its way through multiple galaxies, while another can get so tangled by chaotic motion that it practically vanishes. Some theorists are even exploring a wilder idea that magnetism might be fundamentally connected to dark matter, the invisible substance that makes up most of the universe's mass. Could dark matter particles carry some kind of hidden magnetic charge, shaping the cosmos without ever interacting with light? This possibility remains largely unexplored, a thrilling frontier where cosmology, particle physics, and magnetic theory all converge. And even within the objects we see, the mysteries just get deeper. Take magnetars, for instance. These are neutron stars with magnetic fields so mind-bogglingly intense they can literally distort atoms, fracture the star's solid crust, and even twist the fabric of space-time itself. We don't yet fully understand how such extreme fields are generated or how they evolve. Some might decay over thousands of years, while others remain stable for millions. Their very existence pushes the limits of quantum electrodynamics and relativity, hinting at deeper, undiscovered laws of magnetism. And what about the biggest scales of all? Galactic clusters and the vast filaments of the cosmic web are threaded with faint magnetic fields that span millions of light years. These fields are incredibly difficult to measure, yet they seem to be everywhere, guiding hot gas, influencing the birth of stars, and possibly even affecting the motion of entire galaxies. Could there be some universal principle behind all these observations? A fundamental law of magnetism that operates across every scale, from the subatomic to the intergalactic? Or are magnetic fields simply an emergent property arising from the chaotic dance of charged particles in a dynamic universe? Magnetism remains one of the universe's most elusive forces. We know it shapes stars, galaxies, and planetary systems. We see its fingerprints in radiation, plasma, and charged particles across the cosmos. Yet its ultimate origin, its fundamental rules, and its connection to the other forces of nature remain shrouded in mystery. But understanding cosmic magnetism isn't just an academic puzzle. Its influence touches our lives directly, shaping the space environment around Earth, guiding cosmic rays, and even protecting our atmosphere from the solar wind. Next time, we'll bring our journey closer to home to explore Earth's magnetic shield, the invisible armor that allows life to thrive and discover the profound ways magnetism impacts all of humanity. Magnetism isn't just some abstract force out there in the cosmos. Right here on our own fragile blue planet, it's a matter of survival, a vital shield against the violent storms of space. Deep within Earth's molten iron core, a powerful engine generates our planet's magnetic field, which extends tens of thousands of kilometers out into space. This invisible bubble, known as the magnetosphere, acts like a cosmic umbrella. Its primary job? To deflect the constant stream of charged particles blasted out by the sun, what we call the solar wind. Without this shield, life as we know it would be a constant struggle against a bombardment of radiation. Think about the sun's immense power. Solar flares and massive eruptions called coronal mass ejections can launch billions of tons of energetic particles toward us. These particles race through space at millions of kilometers per hour. If they were to hit our planet directly, they could strip away our atmosphere and irradiate the surface, making it uninhabitable. But our magnetic shield stands in the way. The breathtaking auroras, the northern and southern lights that dance near the poles, are the beautiful, visible proof of this protection. They are the result of these solar particles being funneled along the magnetic field lines, colliding with atoms in our atmosphere and causing them to glow. It's nature's most spectacular light show, and a constant reminder of the invisible battle being fought high above our heads. But the magnetosphere does more than just protect us. It appears to have actively shaped life itself. There are compelling theories that suggest Earth's magnetic field has played a role in the evolution and migration of countless species. Many animals, from sea turtles to migratory birds, seem to possess an internal compass. They can sense the faint whispers of the magnetic field, using these cues to navigate their epic journeys across vast oceans and continents. Imagine a newly hatched loggerhead turtle, instinctively knowing which way to crawl to find the ocean, guided by an invisible force. Magnetism also safeguards our modern way of life. Our global civilization is built on a network of technologies, satellites for communication and GPS, continent spanning power grids, and the internet itself. All of these systems are vulnerable to intense geomagnetic storms, which can be triggered by powerful solar events. By understanding and constantly monitoring our planet's magnetic field, scientists can predict these storms, giving us time to take protective measures and prevent widespread disruptions. In a very real sense, studying magnetism helps keep the lights on and our digital world running. Yet this protective shield isn't permanent or unchanging. It's a dynamic, fluctuating entity. Geologists have found evidence in ancient rocks that Earth's magnetic field has weakened, shifted, and even completely reversed its polarity multiple times over millions of years. These magnetic stripes, frozen and cooled lava flows, are like a geological barcode, recording the history of our planet's magnetic poles flipping. We are currently in a period where the field is weakening, and while a full reversal isn't imminent, it reminds us that our protection isn't guaranteed. A significantly weaker field could expose us to higher levels of cosmic radiation, with potential consequences for our climate, our technology, and life itself. Even the ground beneath our feet is connected to this force. The tremendous engine that generates the magnetic field, the churning, molten core, also drives plate tectonics. The convection currents in the mantle, which cause continents to drift, mountains to rise, and volcanoes to erupt, are all part of the same dynamic system. While the link is indirect, magnetism is a fundamental piece of the puzzle that explains the very geology of our world. Humanity's relationship with magnetism is ancient. Our ancestors discovered lodestones, naturally magnetic rocks, and used them to create the first compasses, unlocking the ability to navigate the open seas and connect the world. Today, we've harnessed this force in incredible ways. MRI scanners use powerful magnetic fields to see inside the human body without a single incision, revolutionizing medicine. And at the frontiers of science, researchers are exploring magnetism at the quantum level, hoping to unlock new forms of energy, create hyper-efficient data storage, and build the next generation of computers. Ultimately, though, the most profound impact of Earth's magnetic field is simple. It makes our planet a home, provides a stable, protected environment where the intricate web of life could emerge and flourish, all under the silent, invisible embrace of this incredible force. It's a powerful reminder that the conditions for our very survival are often governed by forces we can neither see nor feel. So magnetism isn't a distant, abstract concept. It's a protector, a navigator, and a stabilizer. It shapes our planet, guides life, and secures our civilization. But as much as we've learned, we're only just beginning to grasp how our planet's magnetism fits into the grand cosmic tapestry. The same physical laws that create our auroras also weave magnetic fields through galaxies, stars, and the vast empty spaces in between. Next time, we'll journey through history to see how we uncovered these hidden forces. From the first curious experiments with compasses to the massive radio telescopes now mapping the invisible magnetic web of the universe, have you ever wondered about that invisible force that makes compasses point north? Humanity's journey with magnetism began thousands of years ago with mysterious lodestones. These natural magnets fascinated ancient civilizations, who saw them attract iron as if by magic. By the 12th century, this magic was harnessed. Sailors used the first compasses to navigate vast, uncharted oceans, forever changing trade, exploration, and our understanding of the world. For centuries, magnetism was a practical tool, yet its true nature remained a profound puzzle, force you could use but couldn't explain. The scientific quest to understand magnetism took a giant leap in the 16th and 17th centuries. Picture a time of alchemy and early science, where pioneers like William Gilbert began to experiment systematically. In his groundbreaking work, De Magnet, Gilbert proposed a revolutionary idea. The Earth itself is a gigantic magnet. He suggested that our planet has its own magnetic poles, separate from the geographic poles where it spins.
Ow.
This wasn't just a wild guess. It was the foundation for understanding our planet's protective geomagnetic field, linking this invisible force to the very structure of our world. It was the moment magnetism started to shift from pure mystery to a tangible, planetary science. The 19th century was an explosion of discovery that would electrify the world, literally. It all started when Hans Christian Røsted noticed something strange during a lecture. An electric current flowing through a wire could make a nearby compass needle move. This simple observation revealed a deep, hidden connection between two seemingly separate forces, electricity and magnetism. Building on this, the brilliant Michael Faraday showed that the reverse was also true. A changing magnetic field could create an electric current. Suddenly, the two forces were unified into one concept: electromagnetism. This single discovery wasn't just a scientific breakthrough. It was the key that unlocked the modern world, paving the way for electric motors, generators, and nearly every piece of technology we rely on today. For a long time, we thought magnetism was mostly an earthbound phenomenon. We understood it here, but the vast expanse of space, the stars, galaxies, and the void between them seemed empty of its influence. That all changed in the 20th century with the birth of radio astronomy. In the 1930s, an engineer named Carl Jansky built a strange-looking antenna to track sources of radio static. He accidentally detected faint radio waves coming from the center of the Milky Way. At the time, no one knew what it meant, but it was the first hint that the universe was communicating in ways our eyes couldn't see. We had just opened a new window to the cosmos, and we were about to find magnetism everywhere. Decades after Jansky's discovery, scientists figured out what those cosmic radio signals meant. They realized that when high-energy charged particles like electrons spiral around magnetic field lines, they emit a special kind of radio wave called synchrotron radiation. This was the cosmic Rosetta Stone. By detecting this radiation, astronomers could suddenly see magnetic fields across the galaxy. It was like putting on a pair of magnetic vision goggles. Using massive radio telescope arrays, they could map these invisible structures, revealing that the beautiful spiral arms of our Milky Way were threaded with enormous organized magnetic fields. The universe wasn't magnetically empty after all. It was woven together by an invisible cosmic web. Then, in 1967, astronomers stumbled upon another incredible tool: pulsars. These are super-dense, spinning remnants of dead stars that flash beams of radio waves like cosmic lighthouses. As these beams travel through space toward Earth, they pass through interstellar gas and magnetic fields. This journey causes the polarization of the light to twist, a phenomenon called Faraday rotation. By measuring how much the light twists, astronomers can calculate the strength and direction of the magnetic fields the signal passed through. using pulsars scattered across the sky. We confirmed it. The Milky Way is magnetized on a galactic scale, with coherent magnetic lines stretching for tens of thousands of light years. Magnetism wasn't just a local phenomenon. It was a fundamental part of the galaxy's structure. While telescopes looked deep into space, we also started exploring our own cosmic neighborhood up close. Beginning with early missions like Explorer 1 and the legendary Voyager probes, we sent spacecraft to directly measure magnetism in our solar system. More recently, incredible missions like the Parker Solar Probe have dived into the Sun's atmosphere, while the Cluster mission flies in formation around Earth, mapping its magnetosphere in 3D. These robotic explorers have touched, tasted, and measured the magnetic fields flowing from the Sun as the solar wind, and they've shown us how these fields interact with planets. They proved beyond all doubt that magnetism is a universal force, actively shaping everything from the auroras on Jupiter to the very boundaries of our solar system. With all this data pouring in from space and ground-based telescopes, we needed a way to put all the pieces together. This is where supercomputers come in. Scientists can now run incredibly advanced simulations to model cosmic magnetism on scales we could never observe directly. We can watch a spiral galaxy form over billions of years and see how magnetic fields guide the flow of gas, helping to ignite star formation. We can simulate the turbulent, chaotic dance of plasma and galaxy clusters and visualize the vast, visible magnetic filaments that connect them across the cosmos. These digital universes reveal a hidden scaffolding that underpins the structure of everything, showing us that magnetism is a key architect of the cosmos. After centuries of discovery, from ancient lodestones to galactic simulations, you'd think we'd have magnetism all figured out. But in many ways, the biggest mysteries are still ahead of us. We have a good handle on how stars and planets generate their magnetic fields, but what about the very first magnetic fields in the universe? Where did they come from? How did the colossal magnetic structures spanning entire galaxy clusters form and grow? Some scientists even wonder if these grand magnetic fields could be linked to some of the biggest puzzles in physics, like dark matter or other exotic phenomena. The more we learn, the more we realize how much we still don't know. The story of magnetism is a story of seeing the invisible. It's a force that moves silently, without a trace, yet profoundly shapes our reality. We started with a simple, curious stone that pointed north. That curiosity led us to understand our planet, to unite electricity and magnetism, and eventually to map the hidden architecture of the entire universe. From Faraday's simple coils to the Event Horizon Telescope, imaging a black hole, we have steadily pulled back the veil on one of nature's most fundamental and elusive forces. The journey shows that with persistence and ingenuity, humanity can uncover even the deepest secrets of the cosmos. It's a frontier to be harnessed, a mystery to be understood, and a new realm for us to explore. From the explosive birth of stars to the delicate balance that allows life to thrive on Earth, magnetic fields have been the silent architects of the cosmos. One of the most exciting possibilities is just around the corner in the realm of energy. You've probably heard of fusion energy, the power of the stars. Well, magnetic confinement is the key technology at the heart of that research. Scientists are creating incredibly powerful magnetic fields to trap and stabilize superheated plasma, essentially building magnetic bottles to hold a star. If we can perfect this, these magnetic containers could unlock a source of virtually limitless clean energy, forever changing our civilization and our relationship with the planet. It's incredible to think that the same forces governing entire galaxies could soon be powering our homes. Beyond our planet, magnetism could revolutionize how we travel through space. Imagine spacecraft unfurling giant magnetic sails. These incredible devices wouldn't need traditional fuel. Instead, they would ride the magnetic fields flowing from the sun and planets, accelerating to incredible speeds. It's like sailing the cosmic ocean on invisible winds. Furthermore, powerful magnetic shields could protect our astronauts from the constant barrage of deadly cosmic rays on long journeys to Mars and beyond. This isn't just science fiction. It's the future of extending humanity's reach into the solar system, making deep space exploration safer and more feasible than ever before. Our search for life on other worlds also gets a magnetic boost. By learning to detect the magnetic signatures of distant exoplanets, we can identify worlds that have this essential protection. On the grandest scale of all, understanding magnetism could completely reshape our view of the universe. The largest known structures in existence, the vast filaments of galaxies, and the empty cosmic voids are all threaded with immense magnetic fields. We still don't know where these fields came from. Cracking this code might reveal new fundamental laws of physics. It could give us a peek into the very first moments after the Big Bang, and maybe even shed light on the two biggest mysteries in cosmology, the nature of dark matter and dark energy. Think about this. Some theories even suggest that these vast cosmic magnetic fields could be storing and transporting energy across unimaginable distances, subtly influencing the evolution of the entire universe. Could we one day learn to tap into these unseen reservoirs of power? It sounds like something from a far future story, but it's a tantalizing question that pushes the boundaries of physics and our own imagination. Could the empty space between galaxies hold the key to our energy future? The study of magnetism is a journey that connects the incredibly small with the unimaginably large. It links the quantum spin of a single electron to the majestic dance of entire galaxies. From Earth's protective shield to the invisible web that holds the cosmos together, magnetic fields are the hidden scaffolding of our reality. They are everywhere, influencing everything, yet they remain mostly unseen. And despite centuries of scientific discovery, one thing is certain: we've only just begun to hear the universe's magnetic symphony. The questions that lie ahead are profound. How did the very first magnetic fields come into being? Do they actively guide the evolution of the universe itself? And could humanity one day learn to harness cosmic magnetism, using it to power our world or explore the stars? Magnetism is subtle, silent, and invisible. Yet it shapes everything we see, from the light of the most distant star to the very existence of life on our own planet. All around us, the unseen engines of the cosmos continue to hum, their threads woven through space and time, just waiting for us to finally understand their true power. The magnetic universe awaits, invisible, infinite, and ready to be discovered. Thank you so much for joining me on this journey into the invisible forces that shape our universe. If you found this as fascinating as I do, please hit that like button and consider subscribing for more deep dives into the cosmos. We'll see you in the next one.